So another example, y, WTF. And in this case, that is y, the PHYS. WTF stands for all kinds of things. So why are we doing this? It's useful for certain types of collisions. And I'm going to put collisions in parentheses, or in whatever those are. My greatest lecturing moment of my entire life was when I was teaching sophomore physics, and I did nested air quotes. I was like, air quotes, but then in here. Right? That was like, I was ready to retire at that point. I was like, I'm never going to top that. So these are not even air quotes. These are just real quotes. Where mass is redistributed. Ooh, where mass is redistributed. You're too young to understand exactly what that means. Okay. My face. And this is what I told you at the very beginning. Right? We did Newtonian mechanics. You could solve any problem I give you with Newtonian mechanics. F equals ma, torque equals I alpha. But certain kinds of problems are easier different ways. Right? So we said that very beginning we listed that before, after collision kind of problems are best done with momentum. And something's best with energy, I forgot. Now, collisions are with momentum. Before, after often is with energy. But this is even more special. This is a certain kind of a collision where something moves. Okay? So that's what we're going to do. We're going to make something, we're going to change the mass distribution. Okay, so here we go. So the deal is, and we'll do a couple of problems with it. Let's see. We'll have to take a break. So we're on a frictionless surface as usual, and we're standing at the edge of kind of like a, what do I call it? A sled, right? So here we go. It's a standard situation. This is frictionless and icy. And this is the mass of the sled, right? So the sled has some mass, and the person has some mass. Very nice. And we're going to put this sled on a coordinate system here. So the I serves as a coordinate system. That says plus x. All right. And we'll put that where I want the origin? Surely not. Yep. Okay, we'll put the origin there. And we're going to say the sled has a length L. All right. That's it. So here you got one right here. Here's a sled, length L. It's on a frictionless surface. So let's go ahead and just do it first. So what's going to happen is the person walks from 0 to L. Person walks 0 to L. They basically walk to the other end of the sled. So what happens is the question. How does everything move? Okay. And while we're setting it up here, let's think this is an isolated system. But is it really a fully isolated system? Only in the X. Excuse me, very intimate. It's only isolated in the X, but we only care about the X. Right? So what we're going to do is that cart, that's my two little crash cart things hooked together with a board to make them longer. And that's like approximately frictionless. That's another sound of age when you can't get up or get down without going, Okay, so it's pretty frictionless, right? I might fall. If I fall and die, I better see a couple of tears before I go unconscious, or I'm going to be really upset. Okay. So if I walk If I walk from 0 to L, let's mark here. Put your hand right there where L is. You can do it. Just put your hand there. It'll be fine. Put your phone there and then sit back down. How about that? Okay. So that's where I should get if I walk to L, right? Okay. I did prop that. Okay. So I'm just going to walk to L. Oh shit. So I didn't get there. Right? And what if I come back over here? Oh my God. And I went right back to the same place. I'm having to touch this because there's a lot of friction that's making things move. But if I try to walk the distance L, I don't get to L, right? So that's what we're going to calculate. We're going to calculate how far do you really get. Because believe it or not, this is a collision problem, right? I'm an isolated system, and I'm having a collision with this thing. We're isolated, and we're sort of like a push-off collision. It's just like pushing somebody off on the skate rink. Okay? You can get your phone. I'm done breaking your phone. Okay, so let's start. We can get it. We can set it up, and then we'll solve it after. You're just going to have to go through the anticipation. So let's set up what really happened here. Is why did I not make it to L? This was the origin. That's where I started walking. Well, you saw it. The sled pushed back. Right? When I walked on the sled, I applied a backwards force to it, because the only way I can walk forward is to push backwards on the thing under me. So this got pushed back a distance we'll call S. This was the original L. And where did I get? I got to the end, but that's where? L minus S. So that's how far I got. So what we want to do is calculate how far I got in terms of the masses and velocities. It'll be a more efficient use of our time if we started the break early and I erased the boards. So let's do that. Right? If I tried to walk the full length L, I don't really get to L because the thing pulled back by S. So we just want to calculate how far the thing pulls back, but think of it in terms of center of mass and what we learned about momentum. Okay, so let's go through a few bullets here. So one, it is an isolated system, sort of, right? It's an isolated system in X. Right. It's actually not isolated in Y, but we talked about in these problems, you just have to pick one or the other, isolated in X. So there's no external forces. We just have to think about internal forces, or the whole reason with doing it by the center of mass is we don't think about the forces. Right? That's the whole point. Because we don't want to think about the force I'm applying to the board and the force the board is applying to me. We want to think of it in this collision way. So since it's isolated and there's no external forces, the center of mass position does not move. Right? Does not move. Okay. So all we got to do is calculate the center of mass before and the center of mass after and set them equal to each other. We can do that because we're good at calculating the center of mass. All right? So the initial center of mass position is, so this is good practice if you don't remember, it's 1 over the total mass, 1 over m total, times the mass of each one times its position. Right? So I had the mass MP, M of the person. Oh, I wrote it. It was in the glare. The mass of the person times the position of the person is 0. So if we make this the origin, I'm not going to contribute to the center of mass. Plus the mass of the sled times its center of mass. So now we've got to use our sort of symmetry ideas. Where's the center of mass in this symmetric uniform sled? It's in the middle. Right? So this is the center mass of the sled. So we treat it as a point particle there. So we say, okay, it's at L over 2 plus mass of the sled times L over 2. All right. Like that. Okay. Okay, now let's do the final. We don't have to actually do any motion or kinematics. That's the beauty of this. The position of the center of mass final is now I've moved a little bit. So I'm at the position... I'm at the position L minus S. So we say 1 over m total, which is just ml or ms plus mp, right? Just m total, times the mass of the person times L minus S. I'm just sitting there. L minus S plus the mass of the sled. So the sled was at L over 2, but now it's just pulled back by S. All right? L over 2 minus S. And then this one. There we go. Those are those two. So while you're writing those down, some of us don't accept this. Why doesn't the center mass move? How do you know it doesn't move? Because it's an isolated system. Right? That's these two bullets. It is the sled and me are isolated. No external forces. If there's no external forces, then okay. I'm sorry. I wasn't clear. Our initial. I'm clear here. Before I moved, the center mass was in one place, right? We all agree it was somewhere. And then when I walked, I applied forces. I applied internal forces to the sled. The sled applied internal forces to me. We had a big interaction, and we stopped. And the final center mass is in the same place because there were no external forces to move it. It's like the sum of the forces external equals the mass total times the acceleration of the center of mass. Right? This was 0. So there was no acceleration, there was no velocity, it never moved. Right? That's what we're doing. But we don't have to do all the forces and accelerations. That's why we're doing it this way. Okay, let's see. Why L over 2? So the center of mass of the block. Okay, so now we're doing something. We're doing center of mass within. We're doing center of mass within center of mass. Okay. So we're calculating the center mass of the system. The way you do that is you take each mass and you say, where is it? Where is an extended object? At its own center of mass. So this is the Sled's personal center of mass. If I may anthropomorphize the Sled, COM is right there. How do I know? Because it's a bar and it's got uniform mass distribution, so the mass is always in the middle. If I was going to put a force on there that's the weight, I would put it right there. Right? That's the center of mass, L over 2. Okay? And then somebody asked, why isn't it L minus 2 over S? So it's just, this is where I am, right? So it's the center of mass was at L over 2 of the Sled, and everything moved back by S. So nothing is S over 2. Everything moved back by S. Woo! Okay. So you can see this is totally different. We're doing physics here. It looks like we're doing geometry. Right? That's why we do this. So you don't have to think about forces or velocities or accelerations. You just have to think about what happened to the center of mass. Okay, so now we're going to equate them. Okay, when I want to equate two things and I don't want to write them again, that's what this symbol means. Look at that. Yes. Those two are now equal. So now let's cancel some stuff. Since they're equal, we could cancel this term. It's the same on both sides. Okay? Everybody thinks that they won't do well in physics because they haven't had calculus. They don't know calculus. Wrong. It's you don't know algebra. Okay? You know algebra. But being able to do the exam quickly and usefully is being able to do the algebra quickly like this. Watch. You ready? Cancel, cancel. M, this is 0. We don't care about that. MS times L over 2 is in both terms. Boom. Done. Right? So be able to look at this and say, okay, once I distribute this, I know that MS times L over 2 is positive here, and MS times L over 2 is here. It's on both sides. It doesn't go away. It goes away. So I'll just cancel this one. This one is still here. Okay? So the ability to manipulate algebra quickly like that isn't really physics knowledge. It's just it helps you do problems. Because if you write out every step, you'll make a mistake. Right? You're less likely to make a mistake if you write out every step. Let's see. So what's left on this side? Nothing. Right? So this side is just 0. What's left on this side? MP times L minus S, the mass of the person. And what else is left? MS times S. Oh, but it's negative. Don't miss the negative. Minus MS times S. It also helps to have it all written down with notes. That also helps you go fast. Okay. Okay, so then we turn this around and blah, 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 and solve it for MS. So we have MP times L minus MP times S minus MS times S. So that's a big hint to take the two negatives and bring them over here. Right, then we have MP times S plus MS times S equals MP times L. And then visually you look at that and say, algebraically, I know what to do now. I'm going to pull out that S and take the MP plus MS to the other side. And solve for what we asked. How far does it move? MP, the mass of the person, over the mass of the person plus the mass of the sled times the length of the sled. And then we're done. Okay, let's see what questions have come up here. Why is it not, no. What is the 0 next to MP? Is it just L over 2? Well, the 0 next to MP, this is my original position, was at the origin. Yes, so set the origin somewhere good. If I put the origin here, that would really suck, because then this wouldn't have a 0, and I'd have to deal with that term. And then more stuff would cancel. So if you put the origin on one of the masses, it helps you out. Okay, everybody really wants this to be L minus S over 2, so go think about why it isn't. Can we solve this problem using momentum and just assume a velocity? That's what we're going to do next. If you want to do the next part, you can. I got the notes. It's really easy when you have the notes. Just come read them off and write this down. So let's look and see if this is right. Mass of the person over the total mass times L. Let's see. So imagine if the mass of the person were really large compared to the mass of the sled. Okay, so let's think about if MP were much bigger than MS. So this are these approximation things. It's good to kind of get used to, right? So if MP is really big and MS is really small, this is basically MP over MP. Right? This is basically 1. Okay? If that's true, if you look at that, you'd say, well, then S is roughly equal to L. So let's think if I was really heavy and the sled was really light, it would just move under me. Right? If I tried to walk this way L, it would just slide back, and the pull back, the S, the shift, would be the same as the length. So that kind of makes sense, right? If I'm really heavy and the sled's really light. What if the sled is really heavy and I'm really light? What if the sled is like the Earth? Whoa. It's like we're doing this all the time because the Earth is like the sled and we're an isolated system. Dude. Well, if that's the case, then this is really small and this is really small, and it's 0, right? So in that case, it's not going to pull back at all. Right? So you imagine if I was really light, if an ant walks on this, it doesn't pull back. If I walk on the Earth doesn't move back. Right? So you can kind of test. It's good to be able to do this, to think about limiting cases is what we call this. What are the limiting cases of this? If these are similar numbers, like they were, then yeah, it moves back a little bit. If this comes out to a half, it moves back half the length. I think it moved back more. I think I weigh a lot more than the sled because it moved back more than that. All right. Let's see. All right. Can we solve this using momentum and just assume a velocity? Yeah, that's what we're about to do. Because we could ask another question. Is with velocity now, right? Because we don't just do this with position. I don't really have to make the noise. As I move forward, the sled moves backwards, right? So I'm moving forward, I'm walking, I'm making progress, but the sled moves backwards. It should stop. Like when I stop, it should stop, but there's friction that's making it go forward. What if there's friction? Thank you. Just a little late. Try to get with my timing here.